Okay, hello. This is the practice problems for chapter 8. Um, if you saw the practice problems for chapter 7, I actually mixed up which question was conservation of energy and which one was not. This was the not conservation of energy one. This was the work energy principle of work and energy. It says right there. So, oops. Question 1 from the last video was supposed to be in this video, and this question was supposed to be in that video, but it's okay. Uh, that it's okay. Doesn't matter anymore. Okay, so two blocks with masses MA equals 25 kilograms and MB equals 4 kilograms are connected by a cord in the pulley system shown. When the system is released from rest, block A slides down the rough incline with coefficient of sliding friction 0.2. Assume that the cord and pulleys are massless, right? So part A, as we slide a distance d equals 1.3, determine the following quantities: work done by friction, work done by gravity, and rope tension. So let's get started on that. So starting with work done by gravity, right? We have U of G, or sorry, that says friction. Starting with work done by friction, we have U of F is equal to negative mu n and d, because the distance is part of what work is. Now, if we consider our thing here, friction is going to be acting this way, and we have a 4-3-5 triangle. It's a perfect Pythagorean triple or something like that, whatever it's called, right? So gravity works straight down like this, and the normal is like this. So if we take our angle here, it's going to be 4/5, right? Because it's this angle just flipped over to here. So this is an angle of 4/5. Or I mean, that's what cosine of that angle is equal to 4/5. I don't know what the actual angle is because I don't want to calculate it, right? So we're going to have it's equal to negative 0.2 times 25 for the mass, because it's mg, this is weight, right, times 9.81 for the gravity, times cosine of theta, which is equal to 4/5 or 0.8, times d equals 1.5. So we get this all together, which equals to 0.2 times 9.81 times 25 times 0.8 times 1.5, which gives us a work of friction of negative 58.9 joules. 9 joules. And that is our work of friction. So now we need the work due to gravity. So if we look at the pulley arrangement, right? And remember, we want a datum somewhere. We can put our datum like this. So we have an SB, and then we have two SAs, like this, right? So, yeah. And the change in SB is going to be the change in 2 times the change in SA, which is going to be equal to 2 times the distance, which is equal to 3. So we need to keep that in mind, right? So for block A, it displaces vertically d sine theta, right? We go down 1.5 at an angle of sine of theta, so 3/5. So we have U of GA, so gravity of A is equal to mg sine theta d, right? And so m is 25, g 9.81, sine theta 3/5, also known as 0.6, times d of 1.5, which gives us a number 25 times 9.81 times 0.6 times 1.5, which gives us 220.7, or 221 if you wish for your 3 significant figures, 221 joules. And now for UGB, we have the same thing. We have negative, because it moves this way, which is in the opposite direction of positive of the datum. So negative mg And we already got our distance, which we said was 2d. So this is equal to negative, what was our mass? 4 times 9.81 times 3. So this is equal to, so negative 12 times 9.81. This is equal to negative 118 joules. Negative 118 joules. And to get the total UG, we just add these two numbers. So 221 minus 118 is equal to 103 joules. 103 joules. So, and part 3, we want the total work done by rope tension on the 2-block system. So, remember that the speed of B is equal to 2 times the speed of A, which we got from our pulley analysis, which are these lines here. So we note that the total work done here is going to be delta T, right? So half mv squared of A plus half mv squared of B, right? Now we can rewrite this as 2v squared, like that. So we're going to get that this becomes 4, and it's going to cancel with the half, so we get 2mv squared, like this, right? So yeah, and then we're solving for this, so we get that u is equal to, in this case, and this is these two u's added together, by the way. So u is equal to uf plus ug, because we want the total work. So this is the total work, which is equal to, so 103 minus 58.9, which is equal to, let me see, 103 minus 58.9 is 44.1 joules, right? So here we're solving for VA. These are both VAs, by the way, but that's fine. Oh wait, I apologize. I skipped ahead to B in my head. This is B. Oops. So for 3, total work done by rope tension, this is just 0, right? So tension is an internal force, so it doesn't have any work. Internal forces don't do work on the system. So here the U of tension is equal to 0, because internal forces don't do work on the system. Anyways, back to the explanation for this, using the work energy theorem. I apologize. I put that in the wrong order. Anyways, so we have this formula, right? If we want to, so we take this and we're looking for V. So rearranging for V, we can add these together, or no, we can't because the masses are different. So we can factor out of V squared, right? And we'll get U over 0.5 MA, and this is MA, and this is MB, plus 2 MB is equal to V squared, and then we just take a square root out front. So square root out front like this is equal to V, right? So plugging in our numbers, so we have the square root of 44.1 over 0.5, so half of MA, so 12.5 plus 8, so 20.5 over 20.5, which is equal to, so square root of this over 20.5 is equal to 1.47 meters per second. And this is VA, equal to VA, and we know that VB is equal to 2VA, so that means it's equal to, so this times 2 is equal to 2.93 meters per second. And that is that question. I apologize for the mix-up in order, but problem solved now. So on to the next questions. So let me just as you can see, there's only 2 more questions. There wasn't a lot of practice for this unit, this chapter, that makes sense because it's just a continuation of the last chapter with the same concept. So last chapter's practice applies anyways. Send to front. Okay, there. So Q2. A smooth 2 kilogram collar fits loosely on the vertical shaft. The spring is unstretched when the collar is in position A. So here, determine speed when y equals 1. If it is released from rest at A and it is released at A with an upward velocity VA equals 2 meters per second. So we have 2 scenarios here, right? So also, we need to read here smooth and fits loosely. This means there's no friction. So no friction. Friction is little f. No friction in this problem, which helps us immensely, right? And I should have gone over this for this question, but it's okay. So how we want to solve these is draw the particle at the beginning and at the end. So its initial and final positions. Identify what we need, calculate all the energies, and then use the conservation equation to get our unknowns. So let us diagram this here. So it starts here like this. It has a spring, and here's our wall thingy, right? And then it goes down here, still has the spring thing. Spring thing is spring. Still has the spring. It travels a distance of 1 meter. So this is 1m. And here it's v equals 0. This is for scenario 1. We know this is 0.75. 0.75. And if you use Pythagorean's theorem, so you get 1 plus 0.75 squared and then take the square root of 1.75, you get 1.25 meters for this hypotenuse. Or that's not how you get that. What am I talking about? Yeah, the square root of 1.75 is not 1.25. You would use the fact that there is this what am I talking about? Anyways, your datum is up here, right? And then to get this, you have y equals 0 up here, y equals 1 down here, right? Yeah, okay. So you get this because of something. Okay, let me see. So for this, we have a few different equations at each point, right? So we have that using conservation of energy, we have that T1 plus V1 is equal to T2 plus V2, right? And also we should call this -1 because it's down from the datum, right? So keep that in mind. So T1 is equal to half mv squared, and we know that it's at rest. Half mv squared, so it's just equal to 0. V1 is equal to mgy plus half ks squared, right? But we know that at the initial position, y is equal to 0. So it's just equal to half ks squared, which is equal to k is 3. Yeah. So K is 3. And yeah, so T2 is equal to half mv squared again. So we're solving for this v here, right? Assuming v not equals 0. And then v2 is equal to, again, mgh plus half ks squared. And here h is -1 and s is this 1.25 term. So, I mean, not 1.25. It's 1.25 minus 0.75 to see how much the spring has extended, which it extended by 0.5 meters, right? Extended by 0.5 meters. So, and h is -1. So plugging these all into this equation, we get half ks squared, with where s here is 0. Yeah, 0.75. And then we have that, what else we have, is equal to half mv squared plus this term, right? And then if we rearrange everything for the velocity, which is a lot of rearrangement, you do minus 2 terms and then times 2 divide by m and then take the square root, right? Let me just put that into my calculator here quickly. You're gonna get that Vf is equal to 4.39 meters per second, right? And this is for part A, by the way. Part A. V is equal to 4.39 meters per second. So for B, it's going to be the same thing, but we're just going to add on another half mv squared because our V naught is 2. Can I please copy this? This, and then this is like that. So this is it, and this is a V naught, and this is Vf, like so. And recall, the reason that this there's mgh here is 0 is because from the datum is where we consider, away from the datum is where we consider our energy for height. So if it's on the datum, it has no potential energy. So that's why it's 0 for initially, right? So you do, again, another rearrangement, which is, again, just subtracting these from this side, dividing by half m, and then taking the square root of everything. You're going to get, after I calculate this, it's Vf, and I'll just mark that, Vf is equal to 4.82 meters per second. Okay, that's how you solve that question right there. This one is interesting because, mainly because I don't remember where the 1.25 comes from. It's not Pythagorean's because 1.75 square root isn't 1.25. It's I don't know. You can probably use like, you have V naught, you have S final, you have S naught, you have acceleration due to gravity. I'm sure you could find a way to solve that. You don't have time. Yeah, I don't know. I don't remember how, I don't know why I don't know how to solve that, but it's okay because, yeah. Also, I forgot to say that this S is 0 because there's no extension of the spring at that point, right? I forgot to mention that. This S is 0, so you can just like ignore this term as well. Si equals 0. Yi equals 0. So there's no like initial potential energy. This is just equal to 0. So I'll remove this as well because I forgot to mention that. So this is like 0 equals that, right? Because there's no, yeah, so in scenario A, there's no initial energy at all. So yeah, that's how that works. And here we just add on half mv naught squared. Nice. Okay, on to the next question. Q3. So the springs are undeformed in the position shown. If the 14-pound collar is released from rest in the position where the lower spring is compressed 5 inches, determine the maximum compression of the upper spring. Right? So if the springs are undeformed, that means that there's like no extension for them, right? And then it's released from rest in the position where the lower spring is compressed 5 inches. Determine the maximum compression of the upper spring. So these are in feet. These are in feet. And this is in inches. Oh, sorry, these are in inches. I don't know what sometimes I mix those up, but that's okay. These are in inches. These are all in inches. There's no friction on this, by the way. Because, but it's just an assumption we make. We don't have enough info to get like, or okay, if you were to consider the normal force, it'd be like this, right? And then gravity is acting down like this. There's nothing that would exert, like we don't have anything to get the normal force from. So friction is 0 here, right? Because we'd have forces that are purely vertical, while the normal would be horizontal like this, and we don't have anything to calculate that. So no normal means no friction. So we know that it's smooth. So let's get to calculating. So we have T1 plus V1 is equal to T2 plus V2 because we're assuming there's no non-conservative forces. So released from rest, that means T1 is equal to 0. It's down here, which means we have, but the datum is here, by the way, using this as our datum, the floor. So we have a MGH and we have a half KS squared, and that's equal to, so T2 is, well, we're not told that it actually accelerates at all. We just want the maximum compression of the upper, of the upper spring. So we're assuming that it goes from here, and then in its final state, when it's launched, we want the maximum compression. So that means there's no kinetic energy, right? So that's plus another MGH plus half KS squared, right? So MGH1, let me put the 1 here. MGH1 is equal to, so mass is 14 pounds. I mean, that's just weight. So weight is 14, so mg is 14. And h is, we go down here. We've pushed this down 5 inches. This thing is 6 inches long. So that gives us a total compression of 3 inches, right? I mean, what? Not compression. A total height of 3 inches times 3. So that's just equal to 14 times 3 is 42. 42 joules. And then half KS squared. The first one is just half times k, which is 48 for the bottom. So 24 times s of 5 squared. So 24 times 25, which is equal to 24 times 25, 1 less than 625, so 600 joules. And then for the second, the second MGH, so MGH2, this is half ks squared 1. So MGH2 is equal to, again, we have the 14-pound weight. And so for the distance y here, we're looking for the compression x, right? We don't know what it is, or we can call it xb, right? So we have 25 inches. There's supposed to be a bracket here. 25 inches plus we have xb. So 25 inches plus xb times -3. So it's minus 3xb. Because remember, we had like 3 here as like some height difference of when this pushes down on it. So we need to factor that into our xb as well. So we have this 25 minus 3sb, right? And we have that half ks squared. 2 is just equal to, so here k is 10, so 5xb squared. Just like that, right? And sorry, this is not plus xb. So it's 22 plus xb. Not minus 3sb. That wouldn't make sense at all. That wouldn't make sense at all. So 25 minus 3 plus xb, which becomes 22 plus xb, right? So putting this all together now, we get, so on the initial, we have 642 joules, right? Is equal to 5xb squared plus 1422 plus xb, right? And this is a quadratic, so you'd bring over your 642 here. 12 times 22 is 12 times 22 minus 642 is equal to -378. So you'd have 5xb squared plus 12xb minus 378 is equal to 0. And then you solve for xb, which is equal to, so using polysolve, 5. B is 12. C is -378. You get that you get SB of, or what? When did this become a 12? This is supposed to be a 14. Oops. Okay, that was not supposed to happen. 14 times 22. This is a minus 334, right? And then if we properly solve this quadratic now, so 5, 14, and -334, we get that xb is either 6.89 inches or -969, -9.69 inches, right? And well, we know it's not negative because it's going up this way. So we disregard the negative and we get our final answer that xb is equal to 6.89 inches. So those are all the questions for this chapter that I have. Sorry, I was like really disorganized in this video. I apologize for that. I haven't eaten lunch, so I'm hungry, and hunger messes with the mind. Hopefully that sounded philosophical to somebody. Thank you for watching. I hope you learned something. Um, and have a good day. Bye.